All right. This is lecture 7. This is part 1 where I'm going to introduce the reading, the problems, the warm-up problem, and then I'm going to review what we talked about last time. All right, so the reading for today is we had 2 lectures on chapter 14.5, and this is the second of the 2. So we should finish it up. So finish up your reading of chapter 14.5. If you haven't done so already. Second, here are the problems. These are at the end of chapter 14.5, number 3, 5, 9, 17, 25, and 29. And then here's the warm-up problem, which is very similar to some of the problems that I assigned out of 14.5 for last lecture. So you have to find the instantaneous slope of the function f of xy equals 2x squared plus y squared at the point x is equal to -1, y is equal to 1, and in the direction of the vector v, whose x component is 3 and y component is -4. All right? Okay, so what I'm going to do now is I'm going to review a little bit about what we talked about last time, and then I'll post the solution to the warm-up problem. All right, let me erase. All right, so really what we're getting at now is what I consider one of the big concepts for functions of 2 variables, and that's this idea of derivative. So as you've seen in discussion section, when you have a function of 2 variables, the slope depends on what direction you look. And so here what I'm going to do is I'm just going to draw a generic contour plot. So here's my x, here's my y, and these are level curves of constant z. And I'm just drawing, I just sort of drew them randomly. And the idea is, imagine that we're standing here at some point, and let's just give that point a name. Let's call it x sub 0, y sub 0. And then let's suppose that we're interested in the slope at that point in some arbitrary direction. So the slope in this direction, and let's say that that direction is given by some vector that we'll call v. So this direction is defined by a vector v. So the question that we're trying to get at is, how steep is it in the direction of v at the point x0, y0. And you've done a lot of problems like this in section, where generally there you were thinking about steepnesses along the y-axis or along the x-axis. And now we're thinking about steepnesses in just some arbitrary direction that we're going to pick. And what I showed you last time is that we can use linearization to derive a formula. And the idea of where linearization comes in is that when we want to write the slope, which is the steepness, right? That's the steepness that we're interested in. We want the slope of the function. So along each one of these contours, our function f of xy is equal to constant. So our slope is going to be our change in z, or so we're thinking about, this is the function z is equal to f of xy. So our slope is going to be the change in z divided by, we're going to take some kind of step in the direction of v, so divided by the size of that step, which I'm just going to call here L, okay, which is the size of the step that we're taking when we look at this change in z. All right, and so what we did last time was we used linearization to find this, the delta z. And we said that that was equal to the partial derivative with respect to x at this point times the size of the step we make in the x direction, plus the partial derivative with respect to y at that point, times the size of the step we make in the y direction. And then if we take a step of length delta x in the x direction and delta y in the y direction, then the overall length of our step is given by the Pythagorean theorem. It's the square root of delta x squared plus delta y squared. That's what that is. Okay, and so this was the equation that I derived last time, where our step, we're thinking about taking a step in the direction of v, so v is going to be delta x, delta y, or at least point in the same direction, okay? All right, so this is what we did last time. I'm just going to introduce a little bit of notation now. I'm not going to do anything else with this, but just to introduce some notation. And then I'm going to describe some new terminology for this thing. So I don't want to keep calling this slope because it has a different name. All right, so let me erase the board and introduce that new terminology. Okay, so all I've done is rewritten this formula and rearranged it a little bit. And then here tried to summarize what we were talking about. So the slope at this point, x0, y0, in the direction of this vector v, whose x component we can call delta x and y component we'll call delta y, is equal to this formula. It's the partial derivative with respect to x at that point times this x step divided by the total length of v. So the square root of delta x squared plus delta y squared. Plus the same thing for y. So the partial derivative with respect to y times, at that point, at x0, y0, times my y step divided by the length of the vector v. This, everything that I've written here is a mouthful. And so what this is called is the directional derivative. And it's written this way, as a capital D. And then remember that associated with D will be a direction, right? So in this case, I want the slope in the direction of the vector V. So I indicate that generally with a subscript. And then, so in this case, I've written a subscript V to remind myself that I'm looking at the directional derivative in the direction of the vector V. And then I write f, which is what I'm taking the directional derivative of. And then the point that we're taking that directional derivative at. So in this case, it's x0, y0. And this set of symbols means this sentence that I've written here. Okay? So I'm going to end there. That's going to be sort of a quick review of what we talked about last time with the addition of this new terminology. Now I'm going to go and I'm going to solve the warm-up problem, and then I'll come back and we'll talk more about this. All right, see you in a sec. And oh, and we'll finish up chapter 14.5 when I come back. All right, see you in a sec.